This is the video on how MRI works. MRI, or magnetic resonance imaging, is a very important type of bioimaging. It was one of the first types of imaging to utilize something other than the ionizing radiation of X-rays. Not only is MRI considerably safer than other forms of imaging like X-rays or CT, but it also shows soft tissue in much greater detail than the other imaging options. This is due to the different physical properties of the protons in these soft tissues. MRI utilizes physics to identify water content in tissues and measures energy given off by the spin of protons. In an MRI, a giant magnetic field is created around the body. This field, typically 1.5 to 3 Tesla, is so strong that it aligns all the protons in the water molecules throughout the body. Think of the positively charged hydrogen atoms like the Earth. Each has an axis that it spins on, and when under the influence of a strong magnetic field, those axes all line up to face a certain direction. Then, when a radio frequency pulse is sent through, it disturbs the protons, making them point randomly again. This works by emitting a pulse that resonates specifically with just the hydrogen atoms. The hydrogen atoms in different tissues take different times to return to their aligned states, giving off a certain amount of energy that is detected by a large coil, or antenna, in the machine. Because the body has such a large amount of water, the signals given off are large enough in quantity to generate highly detailed images. Computers can then take these signals and render 3D models of the tissues. This is why most soft tissue injuries, like those seen in spinal cords and nerves, muscles, ligaments, and tendons, are all imaged with MRI. Injuries to these structures tend to cause inflammation and the resultant increase in water in the injured tissue. There are two main kinds of MRI. The first is T1 weighted and the second is T2 weighted. These both use different relaxation times, or times from the disturbed state to the resting state. For T1 imaging, the time measured is for the vector of the proton to realign to the up position. In these scans, water is dark, and fat, blood, etc. is bright. For T2 weighted images, the time measured is that for the axial spin to return to its resting state. This results in water being very bright and fibrous tissue being dark. The two types of images appear to be like a picture and a negative of the picture. Another key type of MRI is functional magnetic resonance imaging, or fMRI. This doesn't directly measure the neural activity, but rather tracks the blood flow to different areas of the brain when compared with a control resting state. Since hemoglobin, the molecule that binds to oxygen in the blood, is seen in the differences of RF pulse energies, the difference between oxygenated and deoxygenated blood can be seen with MRI. When we use different areas of our brains, oxygenated blood is recruited, resulting in an activation of the blood oxygen level dependent, or BOLD, response. fMRI is more vague than a normal MRI, but by using them in conjunction and overlaying the BOLD results on the structural MRI, brain function can be mapped for different activities. This can show functional areas of the brain. For example, when the stimulus is vision-based, a large section in the occipital lobe lights up on an fMRI, showing the activation of the visual cortex. This was the first time physicians could see the working areas of the living brain through an imaging study. This kind of imaging was revolutionary to neuroimaging by making detailed soft tissue visualizations as well as providing a safer alternative to CT and X-ray. This ends the video on MRIs.